So good afternoon, everybody, and welcome to this epic online technology meeting on photonics technologies for advanced light sources. My name is Antonio Castello. I'm technology manager at EPIC in charge of lasers and also biomedical topics, and it's a pleasure to welcome you to this online meeting to discuss about the challenges and needs of these advanced light sources facilities. We will talk about synchrotrons, we will talk about accelerator, we will talk about the big laser facilities, and also what is new in terms of developments from the community. So laser manufacturers, also we will talk about gratings, we will talk about synchronization. So we'll cover the different aspects of photonics technologies that could be interesting for these kind of facilities. Just briefly, because the agenda is quite tough today about EPIC, is an association of more than 100 members, both companies and research centers involved in photonics, and our task is to help them to find new contacts, new collaborations, new partnerships, to help with networking activities, to help with access to market reports, to learn about new applications and new market opportunities. And this is the task of the EPIC staff for all these members. Feel free to contact me back if you are interested in knowing more about the capabilities and the benefits, and I will be happy to discuss with you more in detail. And this is more or less the structure of the registration for today. So we have a quite interesting variety of companies registered. So from end users, of course, a lot of R&D, because this kind of facilities research is very important. Equipment manufacturers, of course, components. So we are cover the whole supply chain in the meeting today. And we can go directly with the agenda because, as I mentioned, the agenda today is quite tough. So I don't want to waste more time in my introduction, and I will let you know what is happening today. So we will have presentations from all these companies and research centers, and we will start with Eduardo Granados. He's applied physicist at CERN, and he's going to present the prospect for extreme photon sources and the CERN accelerator complex. So Eduardo, thank you for being here today, for sharing your experience, and the floor is yours. You can share your screen.
Thanks very much for your introduction. I hope you can hear me well.
Yes, good.
Okay, so yeah, as Antonio was saying, I'm going to talk about some extreme photon sources that we're working on at CERN, and in particular into two areas, in the gamma ray source production and also the X-ray source production. And they are based on the interaction of lasers with different types of particles. So in the introduction, we hear about synchrotrons, maybe FELs. They all work with electrons, but actually back at CERN, we have a new experiment that is based on the interaction of lasers with ions, with ultra-relativistic ions. And I'm going to talk a little bit about that because that's a relatively new idea, and there is still not a lot of experimental demonstration about it. And then in the last couple of minutes, I don't have a lot of time today, I will introduce the X-ray sources we're working on based on inverse content scattering, meaning ultrafast lasers interacting with relativistic electron beams. So if we look at the high energy photon spectrum in the X-rays and the gamma rays, we will find a lot of Compton sources, inverse content scattering sources, that they pair different types of accelerators, storage rings, linacs, energy recovery linacs, with ultrafast lasers, and they can achieve photon fluxes in the range up to 10 to the 14 photons per second, depends on the photon energy quite a bit. So, and those, they're trying to compete with very well-established sources like the free-electron lasers, that they achieve much higher photon fluxes up to 10 to the 16 photons per second, but at lower energies, lower energy range, let's say up to 10 to 20 keV. We're talking about here gamma rays up to 1 GeV photon energy, which is interesting for applications in nuclear physics or particle production, like muons, pions, etc., which CERN is interested in. So the first project we have, the Gamma Factory, it's actually aiming to increase not only the photon energy available from free electron lasers by a factor of 10 to the 4, from the 10 keV to close to the GeV, but also 10 to the 7 in this spectral range in terms of photon flux, and up to 10 to the 16 photons per second. So the question we are addressing here is if we can make such a technological leap of 7 orders of magnitude to deliver similar fluxes to FELs, but in the gamma ray section of the spectrum. Just to put things in context, if we calculate how much is the energy of such a beam in terms of power, if we compare it to European XFEL, which is perhaps the most advanced FEL source in Europe, we're talking about comparing about 40 watts of X-ray light to half a megawatt of gamma ray light, just by changing the photon energy from 20 keV to 400 MeV and maintaining the fluxes similar. So if you want a source of light of 600 kilowatts of average power in the gamma rays, you naturally need megawatt class accelerators and megajoule store beam energies. And currently, there's only one facility in the world providing this type of beams, which is the Large Hadron Collider at CERN. So what is the interesting idea here? So the basic idea is to use the Doppler effect twice with ultra-relativistic ions. So we can think about it in the lab frame or in the ion frame. I think it's, I will jump from one to the other to try to make it as simple as possible. But in general, we will have an ion that has been removed many of the electrons, so it's a heavily stripped ion. And then it's colliding, counterpropagating with an infrared beam. And if this is close to the speed of light, obviously it will perceive and squeeze frequency, so it's a Doppler shifted frequency. And if we actually tune the ion speed to this squeeze frequency, we can access resonant transitions in the X-rays. And we can excite this ion resonantly in the X-ray directly using infrared light. Now, this excitation basically fluoresces or de-excites very, very fast. And this emission happens the same thing. So it's the emission from an ultra-relativistic ion, meaning that it will have another boost in the frequency by a factor of gamma, which is the speed of the ion. So you get this very similar to the Compton scattering for gamma square factor here, but playing with a transition. And this is the main trick, that actually, because this absorption process is linear, then the process is very, very efficient. So we try to, we're establishing now the experiment to prove this. And at CERN, we have a bunch of accelerators. The large one here is the Large Hadron Collider. It's very busy, so we cannot do our first experiment directly there. So we're doing a proof of principle experiment with a less energy beam in the superproton synchrotron, which is this other ring here that is only 7 kilometers long. And it has a very convenient area here with a laser room near adjacent to the accelerator to a straight section of the SPS. It's very close to the famous Atlas detector back here at CERN. And the experiment is going to look a little bit like this. We'll have lead ions, which were demonstrated in 2018 in this accelerator. And it will interact with 5 millijoule pulses of 3 picosecond infrared pulses. And 5 millijoules is enough to actually fully excite or have a saturated excitation of the ion bands. And the interesting thing here is that we have 5 millijoules, but the repetition rate of the ions is 40 megahertz. So if you compute the average power that we need for the laser, is 200 kilowatts. Now, 200 kilowatts, obviously, it's not available on the market. And the strategy that we chose is to actually install a Fabry-Perot enhancement cavity, and with a finesse of 10,000, and then rely on a much more affordable laser system that is only 100 watts and produce 2.5 microjoules pulses. And then we inject here, we amplify those pulses in the Fabry-Perot cavity, etc. Now, for a finesse of 10,000, the type of precision that one needs and reflectivity, it's very high. You need a frequency comb. You cannot use a standard modlock laser, obviously, because otherwise we wouldn't stack the pulses inside the cavity. And if you calculate the line width of this frequency comb, it needs to be less than 2 kilohertz. And then the mirrors, they need to be sort of a LIGO style. So this was quite a challenge. And then we contacted a few companies, and we ended up acquiring an ultra-luminous frequency comb from Menir Photonics. I think they will speak today later. So I say thanks for this laser. And now we're working on this also power amplifier to 100 watts with different vendors. And we expect to have this installed in the tunnel in the next few years. And after the interaction happens for the proof of principle experiment, we will have 40 keV photons at 10 to the 15 photons per second, which is already very comparable to the European XFEL. And this is a little bit of an update of the status of this project. We have tested this laser with a Fabry-Perot cavity that was installed in IJC lab in Paris that is used for Photonics, another X-ray experiment. And we already demonstrated above 500 kilowatts of average power of infrared light in a 35,000 enhancement cavity. So if you want to know more about this, please go to this paper and read it. It's actually a very exciting results, and we are actually working now in going close to the megawatt level of average power. Now, I'm gonna switch gears now in the last couple of minutes and tell you very, very fast about a more traditional way of generating X-rays by interacting laser pulses with electron beams. Electron accelerators, they're more commonly linear than circular. And we have a few of them at CERN, and they don't have a continuous temporal structure, meaning they have bursts of electron pulses, at very high repetition rate, at gigahertz repetition rate. And if we want to do the same idea of using an enhancement cavity, like a Fabry-Perot enhancement cavity like this one, to do a very similar experiment, to do Compton scattering, then the laser that you need is quite different. So because we can take advantage of the temporal structure that has bursts and basically charge this optical capacitor, that's how we call it sometimes, this Fabry-Perot cavity, with a burst or a train of pulses. And once it's reaching saturation, then we inject the burst of electrons. And then in this way, we have a little bit of a simpler and less stringent requirement laser for the Compton scattering, because the number of pulses requires here is proportional to the finesse. You can actually put a lower finesse cavity and have actually mirrors with lower reflectivity, etc. So the frequency comb required for this application, it's actually not as thin as with the Gamma Factory. And this is why we were thinking, we team up with a team in Bordeaux in LP2N to develop electro-optic frequency combs that they can work at gigahertz repetition rate, and they generate very efficiently bursts that they can be injected in Fabry-Perot cavities. So the principle behind, I cannot go really behind in detail in the principle, but it starts from a continuous wave stabilized laser, and then a series of modulators, amplitude and phase modulation, and then after compression, we obtain a programmable train of pulses. And this is really interesting for gigahertz repetition rate applications, because we can not only change the repetition rate, but also the pulse duration on demand. And this will be very, very handy once we do experiments with it. And we're actually building a prototype at CERN. And the idea is to use burst amplifiers that we had before and develop this new frequency combs, either electro-optic fully, and combine it with our old neodymium GELF amplifiers that they are still working, and they can reach very high burst energies of Joule-class burst energies, which will be ideal for this kind of application. So I hope it was not too busy, but I just wanted to conclude saying that there's a big interest in CERN in demonstrating these techniques, not only to produce the high photon energy beams, but actually that is the byproduct of cleaning up the particle beams. So in general, this is a useful technique with or without the high energy photons output that we get. We have on one hand the Gamma Factory, which is aiming to produce these 400 MeV photons, 10 to the 16 photons per second. And then we have this inverse Compton scattering X-ray source, which right now it's developed together with electro-optic frequency comb technology. And with this, I would like to thank all of our collaborators across Europe and the world, and you for your attention. Thank you very much.
Thank you very much, Eduardo, for the presentation. So we have time for questions. So you can raise your hand using the button below. You can use also the Q&A chat and box and the webinar chat. So we have time for questions for Eduardo. I can perhaps start with a question regarding the amplifier that you mentioned that you want to combine with the laser from near photonics, that you were looking for different options. Is there any requirement that is particular in your case that could be interesting perhaps for one of the manufacturers here today to know more about that?
Yes, so we're looking for 100-watt average power amplifier, 1030 nanometers, that also doesn't introduce significant phase noise to the laser. So we want to maintain the Menir Photonics oscillator performance, which is almost like a dream, I will say, through the amplification process up to 100 watts. So we want to maintain this performance at, of course, at high average power. That will be one of the keys. And the second one is that it requires very little interventions. So this will be installed in an accelerator facility, which means that there is no access 24/7 to the lab. So it needs to be running nonstop and remote control and all of that stuff. So it's the simpler, the better. That's the rule we usually follow. But
Very good. I don't know if there is any other question for Eduardo. Well, if not, thank you again for a nice presentation today, for being here, Eduardo. And anybody interested, you can contact Eduardo to discuss more in detail any of their experiments that he presented today. And we can move to the second speaker. So it's a pleasure to introduce you Christopher Arrell. He's scientist at the Paul Scherrer Institute, PSI, and he's going to take the photonics technologies for advanced light source at the Swiss FEL. So thank you for being here today, Christopher.
Yeah, thanks, and thanks for this opportunity to try and give you a very brief overview of the different kind of photonic systems, like a taste of the photonic systems that we use and rely on at Swiss FEL, which is part of the Paul Scherrer Institute. So, just an outline. So my role at the institution and my background is I'm responsible for what we call the X-ray photon diagnostics. So all the different schemes and methods we have for measuring and understanding the X-ray pulse that our machines are producing. And as I say, I'm going to give you a highlight of 3 of the photonic systems that we use. But first of all, we've heard about already different types of accelerators to produce X-rays and photons of different energies. And if we want to take out a simple message of what makes FELs different from other types of accelerators, and especially compared to synchrotron accelerators, is that a free-electron laser produces pulses with sort of an unprecedented peak brilliance in the X-ray domain. In this case, FELs can go from the infrared to the very hard X-ray regime, but in this case we're talking about soft and hard X-rays. But the point is that we have very short pulses with very high peak brilliance in ultra short pulses, and importantly with a full transverse coherence. And the key aspect for a FEL to produce these pulses is kind of an ordering process you could think of called SAZE, where by the spontaneous emission of a high energy and accelerated electron that is going through a oscillating magnetic field, the spontaneous light that's produced kind of amplifies itself in a similar way to a laser cavity. Not strictly the case, so but that's where the laser name comes from, so that we have a clear amplification of the X-rays through what we call these undulators. And then with these high peak brilliance pulses, we use them for a range of applications to study biological, physical, and chemical systems, where with a high peak brilliance, we can develop new spectroscopic methods where we can take key advantage of the site specificity that we have with X-ray photons. So just a couple of examples here are developing new spectroscopic methods to take advantage of the short pulse of our X-rays, and also another application is measurement of structural and functional dynamics in biological systems, where you're actually relying on the high peak brilliance to use your X-rays to image of the biological system. But most importantly is that all the photons that go through that system travel through in a short period of time before the system that you're trying to study starts to break up. So this idea of diffract before destroy. So a machine like SysFEL is a 700-meter long machine, so it's kind of in the let's say the medium range of sizes. So a lot shorter than places like European Excel and of course CERN, but then kind of a medium-sized facility where there are different distinct parts, where the electrons, which are accelerated in our case up to about 5 GeV, go through a series of accelerators after the initial injector, and then the electrons afterwards are then also go through a series of undulators, where this oscillation process produces the X-rays, and afterwards then the X-rays can be distributed to a series of user end stations, where the key difference with a synchrotron and the FEL, as well as the synchrotron, can have multiple users using the electron beam at one time. Here you have one electron beam and one user, so the cost per experiment is significantly higher. So at SysFEL, then there are two operational machines where we have two electron bunches that go down the accelerator at 100 Hertz with a slight delay between them. So we have two parallel operations, one in a soft X-ray called Athos, and one in the hard X-ray called Aramis. Now, if we think so as I said, we're cited at the Paul Scherrer Institute in the forest. So it's sort of semi under the ground in Velling Wood, which and nicely kept open to the public, so you can walk right over the building, which is fine. But then it gives us some limitations in what we can do with the electron beam inside the building, where we have the two parallel accelerator lines, we see in the top side. So we use a copper linac for the acceleration, and then these series of undulators down in the blue we see here, where the photons are created. Now, the key purpose really of a short pulse experiment, and maybe which is different when we think about synchrotron type measurements, is often why we care about short pulses, is to follow dynamics. So imagine we have some system where we know we have some molecular system where we have some electron density in state A, and we know it goes into state B. But the question we really need to know is how does that transition take place? So we can do that with a method called pump probe, where we use two pulses, where one of those pulses can be an X-ray pulse. Two of those pulses could be X-ray pulses, but what is more commonly used is one is an X-ray pulse and one is a visible or terahertz or mid-infrared laser pulse. And by initiating some state change from state A with what we call the pump pulse, so that could be, say, a UV photon from a synchronized laser system synchronized to the X-ray system, we can vary the delay between the pump and what we call the probe, which is the red pulse here, which could be the X-ray pulse, where we see some diffraction from the electron state. And by delaying the time between these two pulses and then collecting some variable, what we see is we can delay those, and whilst we will measure a system, we'll measure a blue curve like this that gives us an estimation of how this system changes. So that's the kind of fundamental measurements that we do with the time-resolved FEL. So just a quick overlook of the main photonic systems. The most important, the start of the whole system is that we have a cathode that produces X-rays, and this is done by photo emission of a copper cathode from what we call the gun laser system, where this has to be an extremely reliable system that can run in an environment with which is it's not accessible to the engineers as it's running, and we require an extremely stable pulse energy stability, where on the intensity, the shot-to-shot intensity difference is so 0.005 or less RMS. And the system here is a ytterbium based system of 450 femtoseconds, but only running at 100 hertz, which is the repetition rate of the system. So this is then doubled and tripled to produce a pulse which is then impinges on a copper cathode and produces the initial bunch of electrons, which are then accelerated down the amplifier. The second new application of lasers and photonic systems on the electron bunch is we can actually use an external laser field to modulate the electron bunch itself to make the FEL more laser-like itself. So this requires a large laser system halfway along the tunnel, which is then coupled into the electron accelerator, and the co-propagating intense laser pulses and electron bunches causes a modulation, which is then used to produce very stable and very short X-ray pulse trains. And the laser system that's used there is a 15 millijoule TISAF system, where we require a high pulse energy, but then, to be honest, the kind of the shot-to-shot stability and pointing jitter causes more of an issue. And for a system like this as a facility, then the actual running costs of the large pump laser systems that are required is also a significant cost that has to be calculated when these are used for certain experiments. Another main application of photonic systems, as we heard a bit before, is the timing and synchronization system, which is all laser-based with a whole multitude of systems coming from a 10 megahertz reference signal, where all of the timing diagnostics, the external laser systems that are used in the pump probe measurements, the timing and the we have a unique system for tagging every pulse that we produce with a unique pulse ID, relies on this optical system, which is then distributed over the 700 meters of the facility. And the timing and synchronization is one of the key systems that ultimately gives us the time resolution of our system, of our experiments. We then use similar, different kind of photonic-based systems or optical systems for the diagnostics of the X-rays, where we use a lot of imaging and spectrometer systems to measure the shot-to-shot, so 100 hertz pulse properties from the X-rays with a high fidelity. And another sort of jumping around now, but another important system is what I told you about is the timing jitter. Whilst even with the world's best or maybe world's good timing and synchronization systems, you can't remove the fundamental jitters that exist when you want to use, if you're producing attosecond pulses with your X-rays and want to use an externally locked laser system as a pump probe in that, then you really need to have a single shot ability to measure the timing difference between your laser pulse and your X-ray pulse. One method that we use for doing that is we probe the refractive index based change on a semiconductor, which is actually pumped by the X-ray pulse. And by coming in with a chirped white light pulse, we can see where we see a change in the reflectivity of this material, where maybe this video will play. And as we actually delay the arrival time between the X-ray pulse that perturbs this system and this chirped white light pulse, for example, here between 500 and 600 nanometers, we can measure a small change in reflectivity, and by fitting this edge, we can tag the relative arrival time between these laser pulses down to a femtosecond or a few femtoseconds in our time resolution. So I think just looking for the future, we have at the moment two beamlines running Aramis and Athos, and in the coming within the next decade, we hope to have built a third arm called Porthos, where it expand from 6 end stations to 9 end stations. So yeah, that's what I wanted to briefly share with you today.
Thank you very much, Christopher. Thank you for the presentation. We have time for questions, so you can raise your hand. I have perhaps one further question regarding the type of detectors that you are using. You mentioned the spectroscopic device. Did you explore the possibility of using Q-dot detectors? That is a technology that we saw a couple of weeks at Vision, more and more interesting compared with other traditional detection systems.
No, I mean, so but maybe I should have been at the earlier talks for this. But no, I mean, we use two methods for measuring the X-rays. One is to down convert the wavelength using cesium YAG systems, and then to image with a CMOS detector. And then another way is to directly measure the photon energy with pixelated detectors, which are built in-house, called Jungfrau detectors, where we can measure, say, like 10 to the 4 X-rays per pixel itself. But these latter options, they're very big, very expensive systems, which in a way suffer from a relatively large pixel size. Whereas when we down convert with cesium YAG, we lose spatial resolution from the scintillation process in the material. So there is, I think, clearly a gap in the market where some kind of new small detection system with a high spatial resolution would be ideal for these kind of X-ray sources.
Yeah, very good. Yeah, Xiao, you need to unmute yourself.
Audio, okay. Just one simple question: what is the beam size of the beam, and how is that compared to synchrotron beams?
Well, I mean, the beam size out of the undulators is a couple of hundred microns, but then we focus this down to sub micron level. I mean, with the new 4th generation sources, then the beam size is comparable, but the big difference in terms of fluence and the kind of experiments that you can use is really in the pulse duration. So whilst we can have on average the same number of photons that come out of a synchrotron at a megahertz and each pulse is over sort of tens of picoseconds. Here we'd have the same number of photons in 100 hertz, but over a pulse of 5 to 10 femtoseconds.
Thank you.
Thank you very much, yeah. William?
Yes, thank you, Christopher, for the talk. To continue the Xiao question, do you experience any damage of the optics? Because you said that you are using the same average power almost in the beam, but shorter pulses and higher energies.
Yeah, I mean, you have to be aware of material damage both on a single shot and on the average pulse energy. So I mean, we're kind of luckier than higher rep rate machines at European FEL and places where then with a higher repetition rate, then they really do have to have active cooling on the optics. On Athos, we go to pulse energies approaching sort of 8 millijoule per pulse, and there we have to take care about the footprint on the optics. So certainly it's more of an issue in the soft X-ray. In the hard X-ray at 100 hertz, we don't necessarily go into these problems, but it's getting there. Yeah.
So I think there is no more questions. So thank you again, Christopher, for nice presentation and for being here today.
All right, thank you.
Summary also. And we can move to our next speaker. So it's a pleasure to introduce you. Daniel Peters is the CEO of the company Cycle Lasers. He's going to present the femtosecond precision, synchronization and frequency and time distribution. So Daniel, the floor is yours.
Hello, yeah. Thank you, Antonio. Thank you, Vera, for organizing this nice meeting here. Today I'm talking about our solutions. The first company, I guess, I present here. So about femtosecond precision synchronization. Christopher also already mentioned that this is an important part of large facilities of light sources, and so I will briefly introduce some of our solutions we implemented in the market. So Cycle is often we say we are a startup, but we are not. So we are close to 10 years old. It was founded by Franz Gärtner here in Hamburg. We are all based in Hamburg. Meanwhile, we are 33 people from 13 countries, all here based in Hamburg. And we are delivering femtosecond precision synchronization solutions for small facilities up to large facilities. And now we also deliver for European Space Agency the timing and frequency distribution systems for their deep space antennas. So these are not 33 pictures on the right-hand side. We have to do nearly, I guess, new photos. So just to introduce what we are doing. So our customers are, you know, this for sure, I guess. This is Slack in California. Our customers typically have a clock, yeah, and a large facility, which is here something like 3 kilometers long, and they want to distribute the timing signal to different stages, and especially, and also I think those Eduardo and Christopher mentioned the pump and probe experiments. Of course, you know that. So in the end, in the experimental hall, the users have two different lights coming to the probes, and they want to have it in a very good synchronization and also different time delays between these two pulses. So our main or basis of our company are these two detectors developed by Franz Gärtner and colleagues at MIT a few, not decades, more than 10 years ago, I think. So the balanced optical cross-correlator comparing two pulses of femtosecond lasers. So they are compared in a crystal 2 times so that they are not sensitive for, let's say, amplitude noise or something like that. Then, in the simplest way, the error signal is feedback to the piezo and the motor stage of the slave lasers, so they are synchronized in the order of a few femtoseconds. So we already reached, let's say, attosecond level, at least the measurement of attosecond level, or even better, so at least in a few experiments, is possible. So the synchronization in the end depends also, of course, on the piezo and the stability of the laser. So this is an example of a laser locked to a 15 nanometer laser. Typically, we are working together with Min here. Min here will also present later on. Some similar setup is the Bompedy. So just this device comparing an RF source with a femtosecond laser. And most often our customers have an RF source, let's say a laser, or even only a photon Schwarz is a P100, which is SMA. Forgot the name. So they're used as a master oscillator in these facilities. And then for our systems, we are using an optical master oscillator to build up longer links. And this links looks like that. So here we have the source from the customer. It is the laser is locked to the source, and then we have different lines, and then we are using this PLCs and an optical delay line, partially reflection, so that this link is stabilized, quite precise. And then at the end, the user has a choice to get a RF signal or a laser signal. Or eSync is a device which has multiple purposes. Yeah. So this is here an example of a drift, which is less than a femtosecond in this case, over 2-3 days. And most of our customers and large facilities have 8 or 16 of these links. It's also possible to have another TSP, so a temporized stabilized platform here at the end, so that we will have another 8 or 16 links at the end. Okay, this is a precision not all of our customers need. So meanwhile, we developed a solution, especially this one for users who like to transfer laser signals. Of course, we can do that with pulse, and we do it for European Space Agency with a pulse system. But there are simpler solutions. So we started with this wave product for SLAC. In contrast to PSI, so I was very impressed by this photos. SLAC is built more or less in the desert, and many people maybe know, so doors open or not. So they have a temperature change of plus minus 20 degrees within few hours, let's say 1 or 2 hours when the sun is rising. And the pulse system is quite difficult to stabilize because you always have to meet these 2 pulses. So we developed wave for them to stabilize with less precision in this case, so less than 100 femtoseconds over the distance in California. And meanwhile, especially for our space customers, we also developed some, I think, you know, there's also text. We've developed other outputs. These colleagues from space use different pulse per second, IRIC or tick signals, and they often use 10, 100 or even 5 megahertz. This wave solution supports from 10 or from 5 to 10 gigahertz. So the huge light sources typically have something like 3 gigahertz longer the RF system. So what is important for many of our customers is that you don't lose quality, or at least in an area where you even can't measure that you lose quality compared to a laser signal, and we can do that at about several kilometers. So the yellow line, the black line is a state-of-the-art maser. So these are the requirements from the European Space Agency. And the yellow line shown is the Allen deviation. I think that's not that often used measure, but some of you will know that. Of course, you can achieve much better results if you use a pulse system, but even the wave system does not lose quality when you transfer the signal. So also a request from space is a phase frequency meter, so that they continuously measure the phase frequencies, the phase differences between different inputs. So our new device is a bit simpler. So we have this eSync on request from some customers. Which is similar to a Bombardier or BUC, but with less precision. So we have something like a jitter less than 100 femtoseconds, but let's say far away from attosecond region. And also the drift is something between let's say 10 and 100 femtoseconds. Oops. And you can compare a laser or tune a laser or synchronize a laser to RF source or to another laser, and which is quite useful for some of our customers. Is a user adjustable delay, so you can reach a full delay of 2 pi, and so they can shift their pulses quite flexible. And well, it is more like a plug-and-play system, so it is an automatic search and lock mechanism, graphical interface. So as I mentioned, we are not anymore a startup, so we have a lot of customers here. Shown some. We have strong engagement in China. So indeed, Dalian Light Source was our first customer in 2017. Yeah. Currently, we are building the timing system for the new light source in Shenzhen. For SLAC, we built major parts of this timing and distribution systems. For SACLA, we delivered some of our modules, which is also true, by the way, for PSI, but it was just one module, and the same is true for Eli. So I guess we sold one Bombardier a few years ago. Here some only devices. So Michigan was the first customer who wants this delay shift over a huge distance. Yeah. And these red dots are stations from the European Space Agency, so it's down. Next year we will deploy in New York and in Malagi in Argentina, and also in Kiruna in Sweden. So that's the end of my talk. Thank you for your attention.
Thank you, Daniel. So we have time for questions for Daniel.
Everything is black on my screen here. I don't know. I lost something. Do I still share or do I do not?
No, you are not sharing anymore. But
unfortunately, I can't see you now. But
okay,
we can hear you.
We see you and we hear you. So we have time for questions, as I mentioned, for Daniel. You know, Daniel, what is the big question? That is, what can I do for the others? What can the others do for you? So you perhaps can share of some of the challenges or what you are looking for when talking with these kind of facilities. Perhaps a couple of things that you are looking for.
Yeah, for example, well, I'm more responsible for administration and organization, but sometimes I think we research too much, and sometimes I'm so happy that we research so much. So, for example, we are always thinking about a beam arrival monitor, for example. We could join forces, see what is possible for that. That is interesting for us. And of course, many of our customers are also research partners, let's say. Yeah? So we develop a lot of things together. So we are always open for research collaborations.
Okay, very good. So I don't know if there is any other question. If not, now you can reach Daniel for further discussion. So you can contact us if you want to be introduced to him for discussing any particular topic. So Daniel, thank you very much for being here for the presentation today. And we can move to our next speaker. So I have the pleasure to introduce Roland. Sorry about the surname because it's quite difficult for me as a Spanish. Nagy Mihaly, perhaps I told it right. He's area manager of high-field laser laboratory at the ELI Alps, and he's going to present the ELI infrastructure. So Roland, thank you very much for your time today.
Hi, almost close. It's not Mihaly. Yeah, it's hard to spell. So thank you for the kind introduction. I will just try to share again the screen.
Yeah, working well now.
It's working? So you see my full screen, right?
Yeah, everything good.
Okay, cool. So yeah, I'm working in the attosecond light path source facility of the extreme light infrastructure, and I'm responsible for the petawatt laser actually in this facility. So Alps, I mean the Alps facility offers a large variety of laser systems for different purposes, coupled together with the different secondary sources. Mainly on high harmonic beamlines and also particle beamlines as well. And finally, we also couple a lot of secondary sources with different end stations, like a nanoscale or REMI or whatever. And in the meantime, we also offer our users, since we are a large user facility, we offer also theoretical help with their studies of their experiments in our laboratories with the different simulation tools. And also we can offer a really large pool of metrology for the light sources, the secondary sources, and also next to the end stations. So basically, due to this large selection of available infrastructure, we can offer a large number of different applications basically in our labs, like plasma physics, accelerator physics, attosecond physics, and also nanophotonics, pump probe attosecond experiments, and so on, and much more actually. So since I'm a laser guy, I will focus mainly on the laser sources. In Alps, we have basically a lot of laser systems, which are focused mainly on higher up rate, few cycle path generation. And this means that basically from 10 Hertz, we go up to 100 kilohertz in rep rate, while the wavelength ranges are basically spanning from 800 to 800 nanometer to 3 microns. And also in terms of pulse energy, we can offer from 100 microjoule to several tens of joules. And most of these sources are few cycle lights. So we are on the short end of the path duration range, while many of these systems can be also even carry envelope phase stabilized to drive phase sensitive experiments. In this table, what you can see here, we have with green, I marked the systems which are already offered in the user calls. Actually, now we are offering the 5th user call. I think it's closing today. And with blue, I marked the systems which are still in commissioning. Here on this table, I will concentrate, since I'm responsible for the petawatt activities, I will more focus on the HF petawatt laser system. on this floor plan, you can see our petawatt laser system located in this large laser laboratory here, marked with red. And this shoots basically to the large 2-meter concrete wall bunker, where actually 3 beamlines are being commissioned now. The petawatt system was actually developed by Amplitude, and its key design parameters are the energy, which is 34 joules, and the pulse duration, which is aimed for 17 femtoseconds, and a repetition rate, which is 10 hertz, which for petawatt systems is super high. And this is very demanding in very different aspects of the laser system operation. Right now, we operate the system at the 10 joule compressed pulse energy level with a bit more moderate pulse duration of 23 femtoseconds and the tuned down repetition rate of 2.5 hertz. This is important because at the moment, none of our secondary sources can handle 10 hertz, not even actually 2.5. But from the operation point of view, it's important to mention that the life cycle of the laser system can be significantly prolonged if you operate your amplifiers at a moderate level, until it is not necessary to go up in rep rate and serve the beamlines with really the 10 hertz pulse train. As beamlines, I can define actually 3 different sources. We have a surface high harmonic beamline co-developed by SourceLab and our team. And here the target is to generate millijoule level attosecond XUV pulses. This is already a very demanding task, and the system is, of course, in commissioning at the moment. While the second beamline is for generating GeV electrons, which is called the e-petawatt beamline, in cooperation with JI. And the third beamline is called UFO, or UFO beamline. This is a quite versatile target chamber where basically we can put any type of target and do relativistic intensity experiments, material studies, and ultrafast probing, basically with foil gas liquid targets. And the commissioning is just happening actually right now with the short focal length focusing, and the e-petawatt is with long focal length focusing. So a bit more about the laser itself. We commissioned it actually last year at this 10 joule compressed pulse energy level. And right now we are managing the experimental campaigns. But of course, we are trying to do statistics and performance evaluation. And right now, the energy stability is quite nice. It's typically about 0.8% RMS, shot-to-shot energy stability. And you can see the long-term stability here, together with the spectral stability, which is actually also quite nice. In principle, we can deliver from 10 hertz to single shots by using a really fast mechanical shutter, selecting the pulses from the amplified pulse train which we want. But typically now we operate, as I mentioned, at 2.5 hertz. The wavefront stability is also quite nice. This is not even the best, I would say the typical one. And also it needs to be highlighted that for applications, it's very important to get a clean temporal contrast. And for this, we already confirmed that in the 4 nanosecond temporal window, we have actually a quite clean temporal contrast. Of course, there is always room for improvement, but I think this already confirms that our system is providing really nice pulses in the temporal domain. We also do, of course, internal R&D projects. And one of the core activity is post-compression. We are doing this on several of our laser systems. And I just want to highlight here one nice result, which we obtained with 15 millijoule pulses from one of the silos type systems at 10 hertz rep rate, where we started with 12 femtosecond pulses, and we achieved actually sub 4 femtosecond pulses with 15 millijoule output energy. So it was already, I think, a record at that time. So it's a really nice result, in my opinion. While we are also doing laser development, where we are concentrating on an ultra broadband 100 hertz TISAF laser amplification. And for this, we are using an OPCPA front end together with some not conventional amplification types. And right now we already demonstrated basically 14 femtosecond pulses with the millijoule level. And now we are going to the 10 millijoule level. And later on, our plan is to raise this energy up to the 1 joule level and 100 hertz rep rate to serve neutron generation experiments. During our development of the laser systems and also in the commissioning phase, we built up quite nice collaborations for metrology, for example, with sphere ultrafast photonics in terms of temporal and spatiotemporal diagnostics. Also, very similar activities were found very fruitful with Source Lab regarding temporal and spatiotemporal diagnostics, and also with FemtoEasy in terms of spectral measurements. And what our experience was is that actually these new developments of new types of diagnostics are purely driven by the emergence of extreme light sources. So this is what happened with us, that we basically entered very new spectral ranges. I mean, huge spectral bandwidth due to our fused to single cycle pulse sources. And basically this pushed the boundaries of the development of next generation diagnostic tools. However, since this is an EPIC meeting, I think it needs to be mentioned what we prefer, I mean, what we need actually for operation is, for example, for the pump lasers, what we see is that flash lamps are becoming a bit hard to get for the future. So we need to think about this, and also for the next-gen capacitor banks to drive these flash lamps. And for example, what is special for us is that we need, for example, for the big pump lasers, D2 as a coolant. It's also not easy to get. In case of the amplifiers, we need large aperture, really high damage threshold dielectric mirrors with really large bandwidth. And also sometimes we need to repolish and recoat our TISAF crystals with really high coating quality. In terms of compression, I think many of the high rep rate systems are suffering from the same problem, that the compression gratings degrade quite fast. Typically, all these TISAF systems are using gold-coated gratings. And for this, we plan to operate with some RF, so radio frequency plasma cleaning techniques. But also I need to mention what we need to develop even further. In terms of pump lasers, of course, improved cooling of the laser heads is essential. Together with transitioning to diode pumping, full diode pumping, it's a big task to deliver for high energy lasers and to improve the beam quality. In case of the amplifiers, it seems now that high quality TISAF crystals with large diameters are a problem to get, actually. And also to go down with the pulse duration, we need to increase the bandwidth. But for the large diameter mirrors, the really high damage threshold together with large spectral bandwidth is also not easy to get. And also because of the really high average power due to the high rep rate, the diffraction grating compressors tend to degrade the pulse quality because of the heat accumulated in the gratings. So here also new directions have to be found, and also maybe grating cooling techniques need to be developed in vacuum for the higher repetition rate, high energy systems. Also, as I mentioned, the beamlines typically cannot handle the high rep rate operation. They first always prefer to use single shots, but for the future, high rep rate gas liquid jet targets and or rotating, shifting solid targets need to be developed with really high precision movement. And in the meantime, also we can start thinking about, for example, cooling the targets themselves to provide the same kind of target material at each shot. So I hope I'm in time. So I would like to simply just thank you for your kind attention and open for questions.
Thank you very much, Roland, for sharing also all these needs for further operation of the system. And we have already a question from Christophe Frontales.
Yeah.
Yes, thank you very much, Roland. It's a very nice presentation and very impressive facility. I have a quite specific question. Have you already characterize some of the lasers regarding the spatio-temporal couplings?
Yes. Yes, I can already tell you that for the petawatt, we actually found that probably due to some misalignment, we had, for example, residual angular dispersion in the compressed pulses. We identified this and now we corrected that. And I think now it's much better, but we also characterized the silos type systems. And we also have now made an experimental campaign on the 3.2 micron system. And I think for the first time ever, we characterized spatiotemporally the 3.2 micron pulses. So we have now a quite extensive pool of diagnostics for such measurements. And typically what we see is that before the experiments, it's better to have a characterization because even from day to day, some things can change in the systems, especially with this really high spectral bandwidth. So yeah, we have done.
And the question which comes together is, thank you for the answer, and it's good that you have already accumulated some experience in characterizing some lasers regarding that point. Can you comment about the devices which are available either from commercial companies or from research institutions? Are you capable to give a point of view about that and about the most relevant technique and devices?
Yes, of course. We have actually now two devices, actually three. So the first one, the most, I would say, simple one, is the imaging spectrometer. So we use now two of these from Femtoeasy. So we have basically a visible one from 300 nanometers to 1.1 micron. And we have asked them to develop one which is from 500 nanometers to 1.5 micron. This is a rather specific and expensive one, but it was necessary for post-compressed pulses. And let me tell you, this is one of the most useful things because you can characterize spatial chirp, angular dispersion, and all these crazy distortions in the spatial spectral domain of your pulses. But of course, this is not enough to characterize for experiments. So that's why we went for spatio-temporal ones also. And we have an insight from Source Lab, but also that's a custom one for higher bandwidth. So this is, I think, from 650 to 1050 nanometers or so. It's a quite broadband one. And we also had a collaboration with Sphere Photonics. And just recently, we got a device which is called ICE. This is similar to termites. And this we developed together. And this is also a very broadband one. Basically, whatever the silicon chip of a camera can provide. And the difference between the two is that the ICE works in near field, while the InSight works in the far field. So they can be used in a complementary way, because in case of some systems, it is easier to implement this technique in the far field, so in the focus of your experiment, for example. But in some cases, you can characterize the parts of the system, for example, an amplifier chain, in the near field. So they can be used in a rather complementary way. And together with the imaging spectrometers, I think this pool is a really powerful tool to diagnose any problems in these high-intensity laser systems.
Thank you so much.
Thank you.
Final question from Dominique.
Thank you for the nice presentation, Roland. Very appreciable. Thank you very much. I just have one question. Can you hear me?
Yes, I can hear you.
Yes, okay. Just one quick question. I will contact you because we may have some solution about high LIDT anti-reflective or high LIDT gratings or nano imprint photonics and structures to help you. So I will send you some information shortly.
Okay, thank you.
You're welcome.
Thank you, Dominique. So if there is no more questions, thank you again, Roland, for the nice presentation today and for sharing all this information. Thank you very much. And we can move to our next speaker. So for me, it's a pleasure to introduce you, Pierre-Marie Paul. He's Vice President and Advanced Laser Solution Business Unit Director at Amplitude Laser, and he's going to talk about the laser-driven X-ray sources for non-destructive testing. So the floor is yours, Pierre-Marie.
Yes, can you hear me?
Yeah, and we see the presentation.
Okay. The laser pointer. Well, okay, doesn't matter. Okay, thank you and good afternoon. So my name is Pierre-Marie. I'm going to talk about some of our plans for laser-driven X-ray sources, and specifically dedicated to non-destructive testing for industry. So it's not a technical presentation, but mostly what our plans and what could be grounds for future collaborations with the panel that is present here. So a quick presentation of Amplitude. So Amplitude has been created in 2001 and has been so far a world leader in ultra-short pulse laser systems. We are present in many, let's say, environments, from the scientific institutions to surgical blocks for eye surgery, and to factories in high-tech manufacturing in Asia, for instance. Today we are about 450 employees. Our headquarters is based in Bordeaux, in France, with more than 5,000 square meters of production area, and let's say several hundreds, thousands of lasers installed in the field today. We can share our market or our applications into three different types. The scientific part, which is an important topic for Amplitude, and I'm in charge of this part in Amplitude, with different type of applications and different type of technology. We'll see it a bit later. The industrial applications, where we address what we call real-world applications with displays, semiconductors, and consumer electronics and microprocessing, and medical applications with some very prospective work on proton therapy and X-ray imaging, but also some very big market applications like ophthalmology. There is a strong synergy between our scientific business and our industrial business. This has been the strategy of Amplitude since the beginning, saying that we explore new applications using less laser solutions, so not necessarily product, but we're looking for flexible solutions that can address different type of applications that with different kind of parameters, laser parameters, in order to be able to change them and find the right parameters for an application. And once we have done that, we switch to the exploitation of this application using a more product-oriented technology. For instance, at Amplitude, this is a direct pump ytterbium lasers. And this has been done since the beginning of Amplitude, and especially starting in 2007, where you could see the evolution of our product range and addressing the markets. So from ophthalmology in 2007 to the new application that we are looking for today, we are chasing more today. And we can give as an example aeronautics, metallurgy, and battery applications, which require very high power laser, up to kilowatts. And we have very ambitious programs in this field. So what are we exploring in the scientific part, and always keeping in mind that our ultimate goal is definitely to use this exploration work to definitely address some industrial or medical applications. So the secondary sources, here we are talking mostly about TISAF, ytterbium high energy systems. So we are combining high energy and high repetition rate or high average power laser systems in the gigawatt range, developing UV, visible and mid-IR sources or terahertz sources. In the terawatt range, so LPP, so laser produced plasma, X-ray sources, and ICS sources. And for the particles, using very intense laser to generate giga electron sources or proton sources. What is very exciting right now for the secondary sources is to benefit from the laser wake field acceleration, and we call it revolution because there are a lot of work around laser wake field acceleration, electron laser wake field acceleration right now, because using intense laser femtosecond laser focused into a gas target, we can generate very high energy electrons, and with a gradient which are much higher than in the conventional accelerators. This provides a compact source of accelerator that can be used later on to generate radiations. Converting the electrons into X-rays can be done in many different ways. You can see here the Betatron, Bremsstrahlung, and inverse quantum scattering. So giving each time different sources parameters. So depending on the usage of the sources, one can use one or the other. As you can see, there are different photon spectra, different energy range, the energy range defining the penetration depth of the X-ray, and there are also different source sizes. The source size defining mainly the resolution of the source. And if we compare the existing technology today, what we can see is that for LPP, Betatron, and Bremsstrahlung, to be able to compete or to compare with synchrotron sources or ICS sources, one needs to definitely increase the flux. So the key parameters are energy and brilliance. And to increase the brilliance, today Amplitude is working using its core technology. So TISAF, ytterbium, and now OPCPA, because we have acquired Fastlight, the French company, to increase our repetition rate while keeping the high energy laser systems working. So one of the first, let's say, target or application that we are looking in partnership with several actors is the non-destructive testing. While it is done for many decades with using ultrasonic processes, using radiographic, using lasers is very promising. And there's a lot of work around that. And the key parameter is the radiation source size that will give a very high resolution compared to existing technologies. There are different ways of doing that. So either you doing using the X-rays or for the neutrons. The existing, would say, conventional technology has obviously a lot of advantage today, but none of them are totally, let's say, sufficient to do everything. So you have different different complementary technologies, and we believe that the laser-based secondary sources could have a place with its spot size for a few microns and significant penetration depth. For instance, the micro CT, so micro computed tomography, so precision tomography, is we have the motivation to detect a very small defect on the object that we are scanning or analyzing. So definitely our target applications are in the batteries industry or additive manufacturing or electronics industries. Here, this is an example that you can find in the literature of composite analysis on different type of object using NDT processes. So I'm not going to comment too much on that. These are things that you can find online. And this is here an example of the Gemini using a 7 joule 50 femtosecond at 3 shots a minute. And with 10 shots, you can see that we can make a quite nice radiography of pouch cell battery, and also detect some material defect on the right side. And I went quite fast. Okay. As a conclusion, so synchrotron FELs have opened the way to new modalities for industrial applications. So now there is a growing need for quality control using X-rays, and which require very high precision and fast scanning. With the improving our laser technology, we can open the way to using our secondary sources to do so. Obviously, industrial and medical applications could benefit from this, from the increasing average power. And other technology, we also make a big progress as well. And to answer the question, so what can you do for us and what can we do for you? I think that we have right now some ongoing R&D project, but we are always, let's say, open to new collaboration in this field. So generating secondary sources and different types of secondary sources and study them, and developing the laser technology enabled to complete the studies, and definitely trying to push this into industrial applications. Thank you.
Thank you very much, Pierre-Marie. So we have time for questions. So I have a question from my side. It's regarding the role of amplitude. Is your idea to develop solutions for non-destructive testing, or is developing sources that with collaboration with detector manufacturers and other companies to integrate a complete solution?
No, it's more to integrate a complete solution. So Amplitude still remains a laser company, but we believe that with joining forces with other actors to develop integrated solutions will definitely benefit the community. Yes.
And you mentioned that the batteries manufacturing is something that you are have in mind to do. Is something that could be used online in the production, or is going to be more a stand-up solution for laboratory testing, let's say?
No, first of all, it's laboratory testing, right? To increase battery efficiency, basically. So we have some project around that. First of all, it's a laboratory testing, but then at the end, probably analysis of battery qualities and so on will be the final goal. Yes.
Okay. I don't know if there is any other question for Pierre-Marie. Well, if not, thank you again, and thank you for showing these future projects in Amplitude. And I would like to introduce the next speaker. It's a pleasure to have here Jonas Hedrick, Product Line Manager, the company Menil Photonics. You had already some nice advertisement at the beginning because your laser is used at CERN, and you are going to present your oscillators for advanced timing and amplified seating. So Jonas, the floor is yours.
Okay. Can you see the screen in full?
Everything working, Jonas. Yep.
Perfect. So thank you for the kind introduction. And yes, we've been lucky that we got so much nice and good feedback already. I'm Jonas Hedrick, as Antonio mentioned, Product Line Manager at Menil Photonics, and today I would like to talk a bit about our oscillators for advanced timing and amplifier seeding. So if we look at a very simple example of an accelerator here in a linear form, it can be separated into 3 major sections. It's the particle source, often an electron gun, a photocathode, the accelerator part itself, and the end station where the experiments take place in the end. Of course, all these three parts, all parts in the accelerator need to be precisely synchronized. Many photonics lasers are present in all of these three parts. The Menhir 1030 product line at 1 micron is present mainly in the particle source and also in the end stations for laser-based detection of individual beamlines, and also for the and our Menhir 1550 product line for the timing synchronization of all the devices in the accelerator, which what we've heard and has been super nicely described already by Cycles earlier today. Why are lasers quite often used in particle accelerators? This comes because we bring some advantages with our lasers. It's superior low noise performance, the repetition rate FREP, and also the carrier envelope offset phase FCO can be tuned. So we have actuators for that in the lasers, and it's a very reliable and easy to use plug and play system that has about the size of, I would say, a shoebox. A quick recap on what we are doing. And about the company, Menhir Photonics is a Swiss laser, ultrafast laser manufacturer based in Zurich. We do the whole design and production in-house in our own ISO 4 clean room. And it's a fast-growing company that will reach more than 30 people this year, by the end of this year, which is soon. And this comes due to our values to produce robust and reliable femtosecond lasers that are turnkey and that will satisfy the people who use it. That's why many research facilities across the world, among them are DAISY, the PSI, CERN, SLAC, and so on, are trusting the Menhir 1550 and also the Menhir 1030 already. So why the oscillators? Of course, it's also about the performance of the oscillator itself. We provide repetition rates accessible from 40 megahertz up to 10 gigahertz, which is compared to other oscillators pretty high, with clean soliton pulses that are always below 250 femtoseconds and at wavelength at 1 and 1.55 micron. Here you also see that we get a very nice soliton spectrum at in this case, it's a 1030, but you can imagine that at 1550, it's the same. The laser is passively cooled, so no chiller is required. Here is a picture of an open box. We see that we are following a modular concept that allows to separate individual parts, which makes it easy to produce all these different systems on the same platform. Now, I would like to use the remaining time to go a bit more into the details. Why are these lasers, or into the advantages of these type of lasers that I've summarized here one more time. If you look at the pulse train, so first we look at the low noise performance. So if you look at the pulse train of consecutive femtosecond pulses, we can have different sources of noise. It can be pulse energy noise, which is also called amplitude noise and results in different amount of energy from pulse to pulse. Also, or we can have timing noise, which is in the end is also known as the phase noise of the pulse envelope and will result in a different time where the pulse arises or arrives. If we look at the Menhir laser, we see that the laser is itself already passively quite stable. So we have a very low pulse-to-pulse energy stability, a very high pulse-to-pulse energy stability, and high timing stability due to the innovative architecture that we use in the laser. This is not only enabling super precise measurements in experiments or for amplifier seeding, but also the Menhir 1550 is ideal for timing distribution, what has been described before by Cycles. We also have if you're more interested into that, we have a paper, a white paper about attosecond timing distribution available on our website, where the technology or the principle is described in more detail. Next, we not only have a very high passive stability of the laser system, but it also comes with repetition rate and carrier envelope offset phase actuators. This repetition rate actuator helps to lock to an external reference. Although the laser is quite stable on its own, it can be referenced to a maser or any other timing signal. So all the lasers. And the FCO actuator serves for tuning the carrier envelope offset frequency, which is needed for comp applications, where frequency comp, as Eduardo described before, is needed. This makes it, for example, the Menhir 1030, an ideal source for enhancement cavities. So you can take the laser and lock it to an enhancement cavity. And now I will advertise one more time that with the Menhir 1030, it was possible to, and an amplifier for sure, it was possible to get these more than 500 kilowatt average power, stable output power in the high finesse cavity. A very interesting publication that I can highly recommend to read. Lastly, the lasers are very, very practical, which is also good for the user in the end, because it's easy to use. You don't need any water cooling. You just need 5 volts, 1 amp to put it on your laser table, and it's basically maintenance free. With this, I'm already almost at the end, but maybe a quick overview over the rep rates that we can do. So we have the lasers. Here is the repetition rate range, and the blue diamonds mark the standard laser products that we have. It comes with products from almost 100 megahertz up to 10 gigahertz. The lower area here, down to 40 megahertz, 40 and 80, which is often used so far, is accessible with a pulse picker that we also provide by now. And here, these hundreds of megahertz models are available in free space or fiber coupled, as the customer decides. I want to emphasize that we provide multiple of the frequencies at what many particle accelerators are operated for example, 54 megahertz or around 40 megahertz, which can be reliably produced in a very compact form and then pulse picked to the desired repetition rate. And we also can do higher repetition rates, 1.3, 2.5, and more gigahertz. This at these 2 wavelengths, others are on demand. The pulse duration is always around 200 femtoseconds. And yes, as I said, high pulse to pulse energy stability and low timing jitter. I hope I could show a bit with this talk that we bring some key advantages with the femtosecond lasers for particle accelerators in the 2 product lines that we have at 1550 and 1030. And with this, I would like to thank you for the attention, and I'm open for questions. Thank you.
Thank you very much, Jonas. So we have time for questions. We saw the application of your lasers in the accelerator, but following the presentation from Roland, do you see also application in a facility like ELI? For example, where do you see your lasers that could work in this kind of extreme laser infrastructures?
Yes, I also wanted to at some point talk to Roland in a later stage. We are talking to Eli in Prague already, and we see that, or we think that we could provide a very good service for Eli, for both or all the 3 ELIs actually in the future, for seeding amplifiers if a reliable and low jitter laser is needed.
Mm-hmm. I don't know if there is any other question or comment. Well, if not, thank you again, Jonas.
You're welcome.
You can discuss with Roland more in detail in private conversation.
Thank you for the connection.
Thank you very much again. And we can go with our next speaker. So it's a pleasure to have here Christophe Simon-Busson. He's the product line manager for scientific industrial laser at Thales, and he's going to present the extreme lasers and application at his company. So Christophe, the floor is yours.
Okay, I'm just trying to see if I can share my presentation. Apparently, I don't see it on the Zoom version. Can you use the PDF I sent?
I can use the PDF. Let me look where it is. Do you see my screen already, or?
Not yet. I see. Ah, okay, it's coming. Okay. Okay, so sorry for the inconvenience. Can you go to next slide? So I am Christophe Simon-Busson, working in Thales.
So something is now it's working.
Okay. Okay. Yeah. So Thales is a large company, by the way, but in lasers, Thales is specialized in solid-state pulse lasers, and in particular short pulse lasers. So Thales is not 30 years like shown in the slide, but now 40 years, by the way. And Thales has specialized for a long time. Few years after CPA apparition, has introduced CPA products in the early 90s, and in particular high peak power lasers. So we did introduce a petawatt laser. We reached petawatt 12 years ago with a system at Berkeley in the US. And more recently, 5 years ago, we achieved the 10 petawatt peak power with the INP system in Romania, which is still a world record. I don't have time for this, but another kind of extreme lasers is the lasers we have on a Mars planet, and it's very tiny lasers, very robust, because one of them is working now since 12 years on Mars ground and still working well. So to perform a spectroscopy analysis using LIPS spectroscopy. Can you go next slide, please? Okay, so on that picture, I show some summary about the what we call HPLS 10 petawatt laser at INP in Romania, which is the most powerful laser in the world. So this laser was completed in 5 years ago in 19, and with an extension of beam transport, which was commissioned the year after. So the particularity of this laser is that it has there are two beamlines, two identical beamlines, which are seeded by a single front end based on OPCPA, and it is based on several TISAF amplifiers. You see on the bottom left corner the synoptics of the system. And we developed the amplifier as well as the pump laser. So you see on the bottom right corner the picture of the laser. And for those you want, there is a link to have a sort of guided tour of the laser if you go to use that link. Next slide. Yes. So that's summary of the commissioning we did with the beam transport in 2020. Was done by the way at the time of the COVID, and we managed to do some on-site commissioning tests with the laser, but was also a large broadcasting over the world with Gérard Moreau and 250 scientists attending online, and we demonstrated these more than 10 petawatts. So I'm not going to give many details, but you see below the three series of tension So it was really a 1 shot per minute. If you see the time tag on the x-axis, you will see there are all the shots which have been fired successively, and you see different graphs with the pulse duration. So the pulse duration in that case was in the range of less than 22 frames per second. So please, next slide. So the message I want to give here is this laser is now online from the beam lines, the transport lines were equipped also with focusing parabolas, which were for the 10 petawatt beams that were installed in 2022 and 23. And the commissioning of the 10 petawatt beam was starting in 23. So there were the graph you see here is that kind of experiments, commissioning experiments with the lasers firing on solid targets, and you see that on the graph the proton cutoff energy which were reached for different target thickness. So, and in that case, the laser was used close to the maximum intensity it can deliver, which is basically 6 to the 22 watt per square centimeter, and it's in that case it was a little bit less because the team was using a plasma mirror in order to further improve the contrast. Also, it's already naturally very good. But for proton experiments is the most demanding one, so you need to provide the best possible contrast ratio for the pulses. Can you go to the next slide, please? Yeah, so that's another experiment. It's right now I think some people or all of you know that there is a bit of enthusiasm for laser fusion, since in particular since the results from NIF in 22 and years after. And there were also some startup companies which were appearing in the field of laser fusion. And one of the examples of this company is Marvel Fusion, which is a German company. And the people of Marvel Fusion, they have with Eli NP and us some collaboration agreement, which led also to further improve the laser, but also to provide beam time on Eli NP. And what you see on the slide is experiments done with the 1 petawatt beam. And this year in 24, they have done first experiments. They have made 2 campaigns, one in the spring and one in the summer, with the 10 petawatt beams this time, with the further improved contrast. Of course, it's very recent, so the results are not yet fully exploited. They are still undergoing some analysis, but apparently they are quite promising, and it means that these, of course, there are also beams at Eli, at the other Eli, which can be used also for laser fusion, and there is a big, quite energetic nanosecond beam in Eli Prague, which also very well, very much demanded for fusion experiments. So that means, one is it's important to say that there is some practical experiments for the science, which now these facilities which are online. And I think it was mentioned by Roland that today is the last day for the Eli Eric users call for access, and within this call, I think there's the first time where the 10 petawatt beam from Eli NP is proposed for user access. So it's very important that now so some years ago we developed these lasers, but now they are online and already providing results for the research community. Can you go next slide? So the second part of my talk is application for laser plasma acceleration. So I think we have some common pictures with our amplitude colleagues, and I think that's the right picture. You have you saw it already in the presentation of Pierre-Marie. So just, I don't insist, I think you can go to the next slide because Pierre-Marie was explaining the big advantage of the laser. So what I want to do is to just insist a bit more on this slide. Again, I think Pierre-Marie disclosed one important thing is that to go for practical experiments and practical applications, we need more flux. So we need to increase the repetition rate of the lasers. So that's something we want to do. And in our case, we decided the strategic decision was to keep the titanium sapphire technology because it's naturally providing very short pulses, less than 30 femtoseconds, but even less, let's say, even less than 25 femtosecond is quite a routine way. And we decided to launch a development of a 1 joule 100 Hz laser, so based on titanium sapphire, for a large bunch of applications in science, industry, and medicine. You see two examples. Below you see the logo of Horizon 2020 project, which is called Multiscan 3D. So the project now is well engaged. It will finish next year. So about developing some configuration of laser acceleration, in particular large charge acceleration schemes, in order to go further and to provide some solution for people needing to develop these systems of cargo screening. And there are some companies in the world developing such system for harbors or for borders, and they need some practical solutions. And in that case, they want to move towards the 3D imaging. This is a feature they don't have yet. So laser is not really completely arrived. I think there is still some let's say research and technology development to do, but I think we are now closer. And another application you see on the right is sorry, maybe the picture is not that big, but the idea is also to explore electrons, high energy electrons, as an alternative to X-ray therapy, which is a standard today for radiotherapy, but also to protons. So the electrons have some advantages over protons. They can be easier to accelerate because accelerate protons to 200 MeV, which is the level required for cancer therapy, is a bit hard with lasers. So right now the community is improving, but is not completely there. And electrons are easier to accelerate, and also electrons, they are a bit broader spectrum. They don't have this bragg peak feature as protons exhibit, but it means also that this very sharp peak, you need a lot of control to be sure that it stops where the tumor is. Electrons is a bit softer spectrum, energy spectrum, so it can be a bit easier and safer to manipulate. So we have right now there is a EU project led by Professor Malka at the Weizmann Institute, and Thales is going to provide a laser for the research, and of course that's is not to the point where the medical usage is there, but we are also considering that it could occur someday in the future. Next slide, please. So in Thales, we had launched this development, and we have also a collaboration, a structural collaboration with a very famous French lab, LOA, Laboratoire d'Optique Appliquée. And we have decided to create a joint research lab on Plateau de Saclay, which is called Heracles, which involves also Lully, so for different topics related to high intensity laser and their application. And within this project, so there is a construction of a new acceleration platform. So you see different drawings and different pictures. And so this acceleration platform will have, you see on the bottom right pictures that the laser is going down towards a radio protected area, And there is also room for extension later on with potentially a second radioprotected area. And this platform we are supposed to develop so electron acceleration, but also X-ray, gamma ray production through different techniques, which can be Bremsstrahlung, which can be ICS, and different configurations. So it's a long-range project. We are right now, if you can go to the next slide, we have already, you see in the picture, we have a first laser there. The laser is right now, we have an amplifier running, and it will be online as a compressed beam as a 200 millijoule level. If you see the synoptics on the left. Oh, I have echo. Sorry. I try to go to the end. And an interesting point is that in that case, the pump laser of the TISAF amplifier is a diode pump laser, which means that they makes the overall laser system more efficient than flash pump based systems. Following this 200 millijoule beam demonstration in a few weeks from now, we are targeting to have the 1 joule version with adding a big amplifier, a large amplifier, 1 year after, which means we should have 1 joule available at the end of next year. And regarding the 200 millijoule beams, so we'll have one at this joint research lab at LOA, but also we are working with a company which is developing these acceleration solutions, and also this secondary radiation solution, which is called TOR System, which is an American company. And this, I think the apparition of this company on the market is really the proof that there is a huge potential for these laser-based acceleration and radiation generation solutions. So just, I think I have one more slide to present some results we achieved. So you see that the results of the amplifier. So before the compression, you see on the left the energy after amplifier, also the stability, which is quite good. I heard that in Swiss FEL presentation was energy of 0.8% RMS. Now we can produce 0.3% RMS, which is also comes from the very high stability from the pump from the diode pump pumping lasers. We did some contrast measurement. In that case was very good, because if you see the contrast, only 10 picoseconds before the main pulse is 10 to the 8th, and it was specified 10 to the 6th, and it was 10 to the 8th, so it's almost 100 times better. And the pulse duration, in that case, we took the full aperture, but we're attenuating the energy because we didn't have the vacuum chamber for the compression at full energy, and we got a 23 femtosecond pulse. And I think that's it, and I thank you for the listening.
Thank you very much, Christophe. I will try to go back to the screen. Okay, so Roland, we have a question already.
Yeah, thanks, Christophe, for the nice presentation. I'm interested to know, what do you plan to use exactly to compress the 1 joule?
Oh, okay, it's a good question. Sorry, I was a bit in a rush, so I wanted to precise, and of course, it's something to share with the audience, is that we are developing currently an active cooling solution for the grating. So it means we are going to use gold gratings, but we are going to cool with water the amount of the grating. So not the silica block directly, but its mechanical mount. So of course designing the mount to ensure proper heat transfer. And we did some preliminary tests in about that. So today the time was short, but I think I don't know. We were showing it at some conferences. I was showing it at ILAS in Vienna earlier this year.
Okay, thank you.
Thank you,
And
Roland.
of course, we can be in touch.
Yeah. Any other question for Christoph? I will perhaps finish with a question that what do you need for the photonics community? You are developing really nice solutions, really nice lasers. Are you looking for something in particular, something that comes to your mind that photonics community can help you with?
I would say that was very interested by all the presentation because there is a very nice combination of very, very large, very prestigious research facilities like CERN or like Swiss FEL, and of course, as you have seen, we have interest for applications, and that's typically the people which have developed applications much before us, and with the RF and synchrotron and light source generation. So I think that the message, I think, I don't know if Pierre-Marie will agree, but I think for the laser community, the goal is not to compete with a synchrotron, with a RF accelerator, but more to find some areas, some niche areas where we can bring some added value and do things that maybe the RF technology cannot do or can do with more difficulties. So the idea is, of course, not to introduce competition between the technologies. So I think it's very good if we can talk to these people. Another thing which is very interesting is that we have seen also some presentation of very key technologies. For example, for the synchronization. For that, for example, the synchronization between the two arms at ELI-NP is more managed by the ELI-NP team itself. So I think I cannot really comment and provide the needs in the detail, but I'm sure that the people from ELI-NP are probably already in contact with the cycle, or otherwise we can put them in contact with the right person at ELI-NP, of course. And of course, it's very interesting technology for many of photonics. For us, you know, we are concentrated on titanium sapphire, so it's another wavelength. So for us, we are looking for 800 nanometer, but I think it's maybe also 1.5 micron laser with frequency doubling is also going to provide a good laser to seed amplifiers. So
yeah.
I think that's the community is. I think we would like it to be bigger sometimes, but I think we can also benefit from the fact it's not that big. So we know the companies and the people, and sometimes it can make our life a bit easier to go directly to the right persons.
Yeah, very good. Good summary, Christoph. So thank you very much, and thank you for being here this afternoon. And I would like to introduce our next speaker. We have Martin Smisser, is the head of Advanced Laser Development Department and High-Lens Lens Center, and he's going to talk about the kilowatt class ion pump solid-state laser BBOC or BBOY. You will tell me what's the right name.
BBOY laser. So
BBOY, good.
Yeah. So good afternoon to everybody. I hope you can see my screen.
Yeah, everything good.
Okay, that's great. Yeah, so thanks for the invitation and introduction. Is it working? Okay, so I'm coming from the High-Lens Laser Center in Prague. So we are like a technological center of the Institute of Physics of the Czech Academy of Sciences. Yeah, we are south of Prague. Probably many of you know us. And we are focusing on like development of laser technology and laser application. And we are focusing also on technology transfer to industry. The key technology which we are focusing on is femtosecond thin disk technology, which is based on fully in-house developed solutions. And BVOY laser. That's like a name of kilowatt class nanosecond diode pump solid state laser. We've been developing in close cooperation with the STFC in the UK. So finally, we managed to generate 1.5 kilowatt, 150 joule pulses from that system, and I would like to focus on a bit more details during my talk here. The cryogenically cooled diode pump solid state laser BVOY, it's a result of many years of development. The system itself was commissioned at Highlights in 2016. However, since that time, we are gradually upgrading it. And actually lately there is demonstrated pulse energy 150 joules at 10 Hz repetition rate in pulses which are like tunable from 2 to 40 nanoseconds. The laser is based on like the dipole or mercury technology, so that means we are using cryogenic cooling of several slabs made of ytterbium, which are cladded by chromium acceptable absorber. And up to now, it's still most powerful laser with the pulse energy of 1 joule in the field of that pumped solid state lasers. Yeah, so you see here the like footprint of the laser system. It consists from the front end on the right side and two energy boosters, power amplifiers. Yeah, the amplifiers are both based on the multi-slab technology. The first amplifier contains 4 slabs of ytterbium with different dopant concentration of ytterbium. So they have size, they have like 45 millimeters and 5 millimeters thickness. The beam size in the first amplifier is 20 by 20 millimeters square. And it's a 7-pass amplifier pumped by laser diodes at 940 nanometers. The second amplifier then contains 6 slabs. Again, it's a multi-pass setup, diode pumped. Both amplifiers are cooled by the helium flow, which the helium flows between the slabs of the amplifier, and the working temperature is 150 kelvins. The slab size in the second amplifier is 100 by 100 millimeters square, and we are using the largest ytterbium ceramics ever made, like in the world. Yeah, so it's like quite unique technology. And to the results, so we lately achieved 143 joules in like yeah, so here you see the 60 minutes test of the amplifier. You see the output is relatively stable. We have like no drop of energy, nothing like that. Optical to optical efficiency is approximately 30%, and you see near field and far field beam profile. Still, there is some space for improving the far field profile, so we are working on deformable optics, which will be installed in the system. And yeah, in fact, yeah, this upgrade to 100 and almost 50 joule was possible due to development or because of development of new optical coatings, which are able to withstand 5 joules per centimeter square for large size LIDT. So it was a cooperation of Highlights and optical companies. We were able to do the large size LIDT and develop this like new kind of coatings. Yeah, so the size of the beam you are using for your LIDT test is extremely important in the field of these large size lasers. So the beam itself from the BVOY laser is squared with flat top energy distribution, as you see in the first row. So we integrated a spatial light modulator for improving, yeah, besides some apertures, for improving the profile. But because of that spatial light modulator, we are also able to change the beam to circular. For example, do not, and maybe some other ones. The beam can, or the laser pulse, which is, as I mentioned, nanosecond, can be also shaped in time. So we can change the pulse duration from 2 to 40 nanoseconds, and it can be like flat top, shock compression, RAM, double pulse, or whatever you need for your applications. So one of the key applications for our laser is like laser shock peening, hardening of material surfaces by shock wave. And this one is like extremely important option for optimizing, for example, the laser shock peening. Yeah, other applications are, for example, laser induced damage threshold measurement, and some other one in like particle physics. What is like unique for the behaviour system? Usually in the large beam high power systems, you have problems with depolarization losses. So that's the case also of the behaviour laser. We were suffering from very high depolarization losses in like unoptimized system. The losses were higher than 50% of pulse energy. You see in the first slide, first row. We were able to develop a set of like 4 wave plates, 2 in front of the system, 2 after the system, and yeah, the proper combination of the wave plates is enables us to reduce the polarization losses down to 3% only. So it's like a quite unique way. So it integrates polarimetry, and we developed like a predictive algorithm which helps us to set the position of the optics, because otherwise, yeah, we have 10 Hz repetition rate. So otherwise it would be task for a very long time and like playing with very expensive systems. So we are able to predict the exact position for all the wave plates, and we are able to do the same also for other laser systems. So we are testing this also at other lasers and are able to offer this service also to our colleagues at other large facilities. Thanks to the very good homogeneity and uniformity of both the profile, the beam profile, and the polarization, we were able to convert the output to second harmonic frequency with very high efficiency, 75%, and the peak 80%. So you see also the stability of the conversion is very good after some thermalization. And that's the next world record we reached, 95 joules at 10 Hz at 515 nanometers. So we used LBO crystal for this conversion, type 1 at 30 degrees centigrade. So you see here like the output is very stable, and this is the near field beam profile at second harmonic. The same at third harmonic. So we reached also very good output, almost 50 joules at third harmonic, which is also the record at 343 nanometers, 10 Hz. So the efficiency is 55% of the conversion. So it's a sum frequency of second and fundamental. We have very good stability of the output, like 1% RMS. Still, we are working on homogeneity. It's caused by some like thermal gradients in the crystals. So you see after 60 minutes, there is some small change in the near field profile. So that's what we are further optimizing. And again, we use LBO crystal for this conversion. And the very last thing I would like to mention for this system, we also developed a Faraday isolator. There is no system like that available on the market. So it's also fully in-house design at Highlights. So it uses TGG crystals with compensation, like a partial compensation of thermal stress induced by effulgence by quartz rotator. It contains cooling by airflow. Yeah, so there are several slabs, 2 slabs of TGG, 1 slab of the rotator, and we are cooling it by airflow. So this is how it looks like. So this magnet, which has 3.5 Tesla in the center, and these are the slabs of TGG, the upper figure, and you see the optical scheme of the setup. We were testing it up to 1 kilowatt, 100 joule 10 Hertz up to now. So with the TGG crystals, you see we were able to reach 30 dB or more than 30 dB isolation ratio for a very long time operation. And we repeated later the same test with the ceramic TGG. The results were comparable. The isolation ratio was around 30 dB. Yeah, so it's working in an excellent way. And that's something, yeah, so this like experience, that's something what we can offer also to our partners. So the main applications for this laser are, for example, like industry application. It's a perfect tool for industrial laser shock peening process, analysis of laser-induced damage threshold of plenty of materials. It can be excellent driver for OPCPA system. Yeah, so we are negotiating now or cooperating with the Eli beamlines in Prague about the OPCPA and its development in the future. And it can be also like a perfect nuclear fusion driver. Maybe it's like a diode pump technology with 10 Hz repetition rate. So there is high potential in future upscaling, maybe for this kind of applications. Yeah, so thank you for your attention. And if
Thank
you
you,
have some
Martin.
question, yeah, I'm open to answer.
Yeah, we have
Thank
time
you.
for questions. So, William.
Hi, Martin. Thank you for your talk. About the LIDT test that
Yes.
you are offering at Highlights, do you have like femtosecond lasers to do the LIDT test, or it's only nanosecond lasers?
Actually, we have both. So as for the femtosecond lasers, we have the platform based on the thin disk. It's like a sub-picosecond 900 femto, yeah, what is now available at Highlights, 900 femto to 1.5 pico. Pulse energy like in like millijoules, yeah, up to let's say 20 millijoules, what is now available for this test. This is not really large size, so it's a smaller beam than from the Bevoisher. But we are offering this at 3 wavelengths or maybe 4 wavelengths now. The fundamental, which is meter beamyak 1030, then 515, 343, and also 257. Yeah, we are also doing here fourth harmonic in the femtosecond regime. Yeah, so all this is available. And in parallel, we are offering the Bevoy laser with large size beam and nanosecond pulses also at 3 the fundamental and 2 harmonic frequencies. Yeah, so.
Okay, thank you.
Okay, you are welcome.
Yeah, thank you very much, Martin, for personalized presentation and for being here today, for showing us all your capabilities at Highlights.
Thanks.
And we can go with our last speaker. So we heard about grading several times this afternoon, and it's a pleasure to have William Renard, sales engineer at Horiba Scientific, and he's going to present the grading technologies for advanced light sources. So William, the floor is yours.
Okay, thank you, Antonio, for the introduction. So you see my screen?
Yeah.
Okay. So, I'm working from at Horiba, so in France, near Paris. So Horiba is a quite a big company, 8,000 people headquartered in Japan. And I will focus my presentation on the gratings that we are manufacturing here in France for lasers and also VUV spectrometers or monochromators that can be used indeed for advanced light source. So it's not working. Okay, all right. So Horiba is working on different kind of application. I won't enter into the details, but here for the gratings, we are working in the scientific segment, and we are providing in analytical instrumentation, usually using gratings for spectroscopy, particle size analyzers, and so on. And we are addressing some OEM markets for the spectrometers, high quantity, large quantity of gratings, I would say, and also we have like custom gratings activity that is more focusing on VUV application that requires high quality food customization gratings usually. We have high intensity, high energy lasers application with large gratings manufactured for petawatt lasers. So 10 petawatt lasers, for example, we have this capability at Hariba. And we're also manufacturing gratings for space and astronomy application, but I won't enter into the details for this application. So all the custom gratings are designed and manufactured in France. And in France, Hariba is the center of excellence for optical technologies or photonics technologies for our mother company in Japan. And we are based in Saclay, and the company is very old. It's 200 years old. As we started, the company started its activity in 1819. So for the gratings, different gratings technologies, so I won't enter into the details, but we have two different product, I would say. We have the master gratings and the replica gratings. So master gratings are usually made based on new requirements. So that's custom, always custom design usually. And replica gratings is more gratings that are manufactured in a high quantity. So not so much for lasers or VUV applications, but we have some products that are compatible with the replication process. So mainly we are using the master gratings for this the laser application and VUV applications, and mainly the holographic recording and ion etching process. The other process, mechanical rolling, is not suitable because this is usually providing blazed gratings with a blaze profile, and as it's mechanical rolling, this is giving too much stray light for a lot of applications. So that's why we are mostly focusing on holographic recording and also the application process. So thanks to especially for the masters, thanks to our broad range of capability and our facility, we can do full customization of the gratings, manufacturing the gratings on plain, spherical, toroidal substrates, different kind of materials, and different kind of size, up to 1.45 meters. So I will briefly introduce the laser gratings. It's just like a list of the feature, what kind of gratings we are manufacturing for the laser application. So the first grating for pulse compression lasers was delivered 40 years ago. So it was in 1983 exactly. And so we have a broad experience in this grating manufacturing. We usually, so we can cover different broad of wavelengths from Ti-sapphire lasers, obviously, or PCPA, Italium doped glass lasers. We have a facility that is able, especially, to manufacture very big size gratings, so up to 1.45 meters. We can cover a broad range of groove densities, but obviously custom design is available, is possible upon request. And in terms of optical performances, usually the gratings delivered are delivered with more than 90% diffraction efficiency. The wavefront is depending, the wavefront performances is obviously depending on the size, but we can reach down to lambda over 20 RMS. And we can consider different kind of substrates, so mainly fused silicon, but also we can consider ultra-low expansion glass like ULE silica or also zero dur. So this is our capabilities for the grating manufacturing. What we offer, we have the manufacturing, but also the metrology tools we have several interferometers to measure the wavefront. And we have here an example of a 1 meter size wavefront map as an example here. And on a meter size grading also, we have this kind of measurement for the efficiency. So for the next slide, I have a couple of video just to show if it's working. Okay, so this is here to show a little bit our facility. So in that first part is the substrate. When we receive the big substrate here, it's an example of 1 meter size. And we start with the cleaning process. So this is here the handling into the equipment to clean the grating. Okay. So after the cleaning of the grating, we okay, that's not working. Oh, that's the shame. This is the most interesting part. Okay, I will do like this. Okay. So we have the photoresist deposition and the control of the thickness, and then after the recording we do the measurement of the wavefront performances of the grating, and this is thanks to our big interferometer, which is a 32 inches aperture. And after the last step, I would say, is the checking the groove profile with our custom-made atomic force microscope, and also measuring with the same benches the grating efficiency. So this is our facility and our broad range of equipment to manufacture such big gratings for laser and especially petawatt lasers at Haruba in France. So now, the lasers can be used for secondary sources, and so for at some point it's necessary to have like a metrology stuff to analyze the feature, the experiments. And we are providing VUV and soft X-ray gratings for monochromators and spectrometers for a while, to mainly for synchrotrons, obviously. So what can we do is based on the customer requirements. So we can of course define with the customer the substrate parameters. We can propose and adjust the variable line spacing in order to correct the aberration, and adjust the recording setup for the grating manufacturing. And we do the groove profile optimization and the grating efficiency calculation. So this is thanks to our dedicated R&D team working on this. And what we offer for VUV gratings, so we provide laminar gratings. So this is I would say top hat groove shape for this kind of grating. We are able to manufacture state-of-the-art substrate with very low slope errors, like in the no, it's not in this example, but for the roughness on the right here, we are able to manufacture down to 0.3 nanometers roughness substrates, and this is very important for VUV application for the diffusion and the strellites. We are well known for our tight manufacturing tolerances for the gratings compared to the competition, and we can either offer busters or replica gratings. Replica gratings, as I said, is mainly interesting in case you have a couple of equipment that are requiring the same gratings for each. And something unique that we offer is the variable groove depths gratings. So we can change linearly the groove shape, the groove depths, along the gratings. And in this short video or picture on the middle, bottom middle is you can cover a broad range, like 1 decade in terms of photon energy, with the highest, I would say, efficiency possible, thanks to the adjustment of the groove profile. So the last talk. So first, thank you to stay after the end of this meeting to listen to my talk. What we need and what we can do and what we can do. So for the lasers, we are still working and assisting the community, because there is the increase of the average power of the lasers. But unfortunately, we are not compressor manufacturers, so we can do what we can in terms of grading optimization. And for the VUV and the soft X-ray gratings, we can help it in different ways, as we have some experience manufacturing monochromators and spectrometers in the VUV, but not only in the VUV. We can help to custom VUV system according to what we can offer in terms of VUV gratings. We are also looking for collaboration, I would say, to do like a LIDT testing on the VUV gratings, because like for the lasers, the power and the energy of the secondary sources are increasing, and we are interested to see where we stand in terms of LIDTs for our gratings, for the coatings, for our master gratings, but also for the replica gratings. And I'm also looking to hear from the community what are the future challenges regarding the gratings for the VUV and soft X-ray. Looking for, as an example, high group densities to get a higher resolution for the spectrometers or whatever else. I will be happy to discuss that with some of you. So thank you for your attention, and if you have any question, and if we still have time, I will be happy to answer.
Thank you very much, William. We have time for questions. Sorry that we are a little bit late than expected, but we have time for questions for William. I have one question regarding the materials or the fabrication process, because we saw this increasing in the power every time. You mentioned in your presentation some materials, but do you think you will need to change a little bit any manufacturing process or the material, the substrates, for example, to do the gratings? Do you expect to keep more or less the same and improving perhaps the quality, or working more in the optimization of the final product?
No, you are right about the first for the substrate with the power increase, and this is something that we already provide to the market, is to manufacture the grating on the ultra-low expansion glass instead of fused silica. So in order to be more resistant regarding the thermal loading on the grating. And with gold-coated gratings, so the gold layer is absorbing 1 or 2% of the light, and so we can't fight against that. We need to accommodate our, I would say, the substrate and so on. And another way is also to work on another grating technologies like multi-layer dielectric, and that was also mentioned in the presentation. And this is something that we are also looking for.
Mm-hmm. Very good. So I don't see any other question, not in the chat. So thank you very much, William, for the presentation and for being a little bit later today in your presentation. But yeah, it's very interesting to know what's happening with the gratings that we hear a lot today in the facilities. So thank you again. And thank you to everybody that for being here. Thank you to all the speakers today. As Christophe mentioned, it's very interesting to understand what's happening in this community and how you can collaborate. And EPIC is happy if we can a little bit do this kind of networking opportunities for all of you. If there is somebody interesting that you didn't reach in the questions, please let me know to introduce you. And I hope to see you in a future EPIC event. Just want to share a final slide because I didn't want to do it before with the next events. So it's anything that is in this slide is future things that we are going to participate on. We will be in the Semicon, Compamed Medica, Precision Fair, Photonics West, of course. But combined with our technology meeting, the next one is going to be diagnosis and treatment with focus in cancer. So perhaps interesting for some of you that were developing solutions for this topic. And of course, more online technology meetings and also marketing and technology reports. So I encourage you to go to our website to check what's happening. And I hope to see you again in the next event. And with this, I want to close the session. Thank you very much for being here today, and a pleasure to have you here, and see you next time.
Thank you, Antonio. Thank you all.
Thank you all for the